Let's move on to our quantitative analysis now, which brings us to Faraday's law. We know that in a circuit, Ohm's law applies, so V equals IR. That tells us that current is potential over resistance. So current induced in a loop, I, is equal to the induced potential divided by the resistance. So the induced potential, we know that it's related to magnetic flux, and I've got a clip of a PhET simulation running down in the bottom. When your magnet is still, it doesn't light up. When the magnetic field changes, the light bulb does light up. So how is the induced potential epsilon, or the EMF, how is that related to the change in magnetic flux? That's what Faraday's law states. Faraday's law states that the magnitude of the induced potential is equal to the change in magnetic flux with respect to time. Now this expression is for a single loop of wire. And this expression gives the magnitude. If we wanted to find the magnetic flux, not just the magnitude, we would include the number of loops times the change in magnetic flux with respect to time. And we know that the induced potential always acts to oppose the change in external field. So we include a negative sign there. So this is the expression we use when we can find induced potential from a function. So we use this when flux is a function. If we just have two discrete points, we wouldn't have to do a derivative. We could say that our change in potential is minus n delta flux over delta t. So we would use this if we had discrete points. But they both say the same thing, and that's that induced potential comes from a change in magnetic flux. One thing I'm going to warn you about here, the book talks about direction, but you have to be really careful. It also talks about direction of flux. But flux and potential are both scalar quantities. We can't have a potential that points in a direction because it's not a vector. So be really careful about that and keep that in mind if you're reading through the textbook. The negative sign, all that's telling us is that the new field opposes the change in field. Okay, so that's what that negative sign refers to. Let's do an example now that pulls together our Faraday's law and our Lenz's law. We have a loop in a magnetic field that points out of the page, and we have a graph that shows that the magnetic field increases from zero over time. Let's try and find the induced magnetic field, the induced current, and the induced EMF around this loop over time. Okay, so the existing magnetic field is out of the page. And our graph shows that it goes from zero up. That means that our existing magnetic field is increasing. So the magnetic field points out of the page and it gets bigger. Nature doesn't like that change in field, so it's going to induce a new magnetic field to offset the fact that the field pointing out of the page gets bigger. The way to offset that field is to make a field that points into the page. That's going to cancel out that increase in field. So there's our B induced. Okay, if the induced magnetic field is into the page, what does that tell us about the current? You make a little circle with your fingers. Your fingers should point into the page for the center of that loop. Then if you're looking at the bottom of the loop, your thumb should be pointing towards the left. So that would be the direction of the induced current to get an induced field in the direction shown. So there's your induced current. And that is the clockwise direction. So it would come down here, up here, and to the right here. So there's the induced current around that loop. All right, how are we going to find the size of the induced potential? That's where we'll bring in Faraday's law. the magnitude of the induced potential is the number of loops, we just have a single loop, times the change in magnetic flux over the change in time. So delta flux over delta T. I've got 2 points here that I can read on my graph. One point is 0.5 for a magnetic field and 0.01 for T. Another point is 0 and 0. So I do have 2 discrete points, so I can use my discrete form. I'll have to remember here that flux is equal to B times A. I'm going to assume that my area vector is parallel to my magnetic field vector because we know that area is either into the page or out of the page, and I'm trying to find the magnitude of the induced potential. Okay, so change in flux is my final flux, subtract my initial flux. That's divided by my change in time. Flux is B times A. Those guys are parallel, so we get B times A. So flux is B final times area minus B initial times area. Our area doesn't change, so that's the same for both terms. Take our area outside of delta B, and then that's over delta T. Okay, so delta B is going to be our B final, take away our B initial. Delta T is T final minus T initial, and area, we have a square loop 2 centimeters on a side. So area is 0.02 meters times 0.02 meters. Delta B is 0.5 teslas, subtract 0 teslas. And that's divided by delta T, which is 0.01 seconds, subtract 0.0 seconds. You could also recognize that delta B over delta T is the slope and calculate the slope. It's exactly the same workings, just a slightly different way to think about it. When you do all that in the calculator, you should get an induced potential of 0.02 volts. So that's the amount of potential induced around that loop when the field increases as shown. So here's a homework example for you to try. You need to find the magnitude of the induced potential as a function of time. You're given a magnetic field. You see that your magnetic field is a function of time. So this time to find your induced potential, you're not going to be able to do delta flux over delta time because you don't have 2 discrete points. You're going to have to do d flux over d time. You're going to have to take the derivative this time. I won't include this in the video, but I will write up a solution and include that one. So since induced EMF depends on the change in flux over time, we can get an induced EMF in 3 different ways because there are 3 ways you can change the flux. You could change the magnetic field, you could change the area, or you could change the angle between the magnetic field and the area. In this example, we have a circular loop with a variable radius. That means in this loop, the area is changing as a function of time while it's in a uniform magnetic field. So let's find the induced EMF in this example. First thing we'll do is make a quick sketch. So we have a circular loop. So we have one single loop. It's shrinking, so it has a radius that depends on time, so we'll call that R of T. It is in a magnetic field, and the loop is perpendicular to the magnetic field. So the plane of the loop is perpendicular to the field. That means the area is parallel to the magnetic field. So our B looks like this. Let's draw in our area vector too. Doesn't say which way the area vector is. I'm going to write it in as pointing upwards. So there's a nice sketch of what we have. We want an expression for the induced EMF. So the induced EMF is minus d phi dt. So we've got minus d by dt of the scalar product between magnetic field and area. Scalar product is minus d by dt times the magnitude of B times the magnitude of A times the cosine of the angle between A and magnetic field. That angle is 0 because they're parallel, so that leaves us with minus d by dt of B times the area. Okay, so let's fill in that stuff next. We've got minus d by dt. The magnetic field is B. And the area, it's a circular loop, so area is pi times r squared. So let's fill that bit in next. what we know about our r. So d by dt of b times pi. The radius is given up here, so we've got r naught, that's a constant, e times e to the minus beta times t. So beta and r naught are just constants. T is our variable here. And that whole expression is squared. So that gives us minus d by dt of b times pi times r naught times e. When you have our r naught is squared and e to the minus beta t is squared, so that's e to the minus 2 beta t. Okay, we just have to take this derivative. For our next step, let's take the constants out front. So we've got minus b times pi times r naught squared times the derivative of e to the minus 2 beta t. When I take that derivative, I get minus b times pi times r naught squared. E is probably my favorite thing to take the derivative of because you still have your e term. Then you multiply by the derivative of the exponent, which would be minus 2 times beta. Okay, let's kind of pull that together a little bit. So minus times minus gives us a plus. I'll pull that 2 in front. So I've got 2 times my magnetic field B times my constant beta. Then I've got my R naught squared times e to the minus 2 beta t. Okay, so if you notice, r of t was equal to r naught times e to the minus beta t. That means this whole expression here, that's just r squared. Okay, so let's fill that last part in. So our induced potential is 2 times the magnetic field times beta. Oh my goodness, I dropped my pi. There, I've got a little bit of space. I'm going to squeeze that back in there. 2 times b, the magnetic field, times beta, the constant, times pi, times r, which is a function of time, squared. So there's my expression for the induced EMF as a function of time t. If you wanted to, you could think about what happens as t goes to infinity. So what happens after a long time? So if t goes to infinity, our radius goes to 0 because r depends on e to the minus beta t, so that goes to 0. If r goes to 0, then the induced EMF goes to 0. And that kind of makes sense. If your loop shrinks to the point that it disappears, it's no longer going to have a potential difference. For this example, we've got a square loop set in a variable magnetic field. We know the resistance, and we're going to try and find the size of the induced current at a specific time. So let's draw the loop first. It says we have a 20 centimeter by 20 centimeter square loop. I guess the word square is redundant, isn't it? It's lying in the xy plane, and its bottom edge is on the x-axis. So let's draw that. So it's just a square turn of wire. Along this side, that's 20 centimeters, 0.2 meters. Along this side, also 0.2 meters. And the magnetic field is parallel to the z-axis, and it's given by b equals 0.8 times y squared. Y is your y variable, times t, and t is equal to time. Doesn't give a direction for magnetic field other than it's parallel to the z-axis. I'm going to assume that means parallel and not anti-parallel. So I'll draw my magnetic field coming straight out. So there's the magnetic field vector. Okay, what is the size of the induced current in the loop? Let's think about how we're going to find that. We know from Ohm's law, V equals IR. That tells us that our induced current is the induced potential epsilon divided by the resistance. And we can also use Faraday's law. It says that the size of the induced potential is minus d phi dt, and we take the absolute value of that to get the magnitude of the potential. It doesn't ask for the direction of the induced current, we just want the magnitude. Okay, so if we're going to use this approach, we need to find d phi dt. Before we can take the derivative of it, we better find out what phi is. So phi is our magnetic flux, and if our b were constant, we would just do b dot a. B is a variable though, so we have to do the integral of b dot dA. Okay, our b is going to be easy to fill in. We're given the equation, but we're going to need to know what is dA. So dA is an area element of our loop. We need to pick a suitable area element. And what we could pick is a little rectangular strip of our loop. So the area vector of that strip is going to point straight out. So there's a little bit. dA points straight out. And the magnitude of dA is length times width. The length is 0.2 meters, so length times width. Times the width. The width is a little bit in the y direction, so the width is dy. Okay, looks like we're all set here. So let's fill in what we have for our b dot dA. So b dot dA is the magnitude of b times the magnitude of dA times the cosine of the angle between them. We've assumed that they're parallel, so the angle between them is 0. So we've got the integral of b times dA. So let's fill in b times dA. So b is 0.80 times y squared times t. There's our b. Times dA, length times width. So for our length here, rather than write out 0.20 meters the whole time, I'm just going to call that L. So L times dy. Okay, so let's see what we'll do next. Why don't we pull our constants out front? 0.80. Y is a variable, so y squared has to stay inside. T is constant with respect to y, so that can come out front. L is a constant, so that can come out front. So I'm left with the integral of y squared times dy. Before we go any further, we're going to have to put in our limits of integration. So y begins at the bottom of the loop, that's where y equals 0, and y stops at the top of the loop, that's where y equals 20 centimeters or 0.2 meters. Okay, next step is to evaluate the integral of y squared. So I've got 0.80 times t times L. The integral of y squared is y cubed over 3. That's evaluated at 0.2 meters and 0. So I've got 0.80 times t times L times y cubed 0.20 meters cubed over 3 minus 0 cubed over 3. And my L is also equal to 0.20 meters. And when we put all that in the calculator, we should get, hang on, I'm just going to grab my calculator and find what that works out to be equal to. So I get 0.8 times 0.2 times 0.2 cubed divided by 3 equals 4.27 times 10 to the minus 4 times t. So there's an expression for my magnetic flux as a function of time. Okay, now that I know the flux, I'm all set to find the induced potential. After I get the potential, I'll be able to find the current, and we'll go on to the next slide since we've got this one filled up. So let's use our expression for induced potential now as it relates to the magnetic flux, and let's find the magnitude of our induced potential. So we'll fill in what we found for induced potential on the previous slide. So we're taking the time derivative of 4.27 times 10 to the minus 4 times t. That's a pretty easy derivative to do. So that's going to be the magnitude of minus 4.27 times 10 to the minus 4. And the magnitude of that value will just be the positive value. So the magnitude of the induced potential is 4.27 times 10 to the minus 4 volts. Okay, next step and final step is let's find the induced current. The induced current is the induced potential divided by the resistance, 4.72 times 10 to the minus 4 volts, divided by the resistance that was given as a half of an ohm. And when we put that through the calculator, we should get for our induced current 8.5 times 10 to the minus 4 amps. Now the last thing to notice is it asks what is the size of the induced current in the loop at 0.5 seconds. Notice here that the current doesn't depend on time, so this induced current is constant. So this is true for all times. If you can hear singing in the background, that's just my husband. He's a very singy sort of person, so every once in a while a tune might happen across our lectures. Okay, so there's our current in the loop, and this is true at all times, so it's also the current at 0.5 seconds.